Imagine a world without pipes, no running water in your home, no way to efficiently move fluids across distances, no grand cities thriving with sanitation. Today, we take pipes for granted. But thousands of years ago, visionary builders solved this problem with nothing but their hands, clay, fire, and sheer brilliance. Today, we journey back to the very first pipes ever created by humanity. Along the way, we will explore the breathtaking old-school construction of pyramids, bridges, aqueducts, monuments, and more. This is the story of how ancient engineers changed civilization forever. Stay with me for this epic tale. Let us travel back, my friends, to around 4000 to 3000 BCE, to ancient Mesopotamia. This land, nestled between the mighty Tigris and Euphrates rivers, is often called the cradle of civilization. Here, the Sumerians and later the Babylonians faced constant challenges from flooding rivers that brought both life-giving water and destructive inundations. They needed reliable ways to manage irrigation for their crops and to handle waste in their growing settlements. It was in this context that the very first pipes known to humanity emerged. Picture the artisans at work along the riverbanks. They sourced the highest quality clay, rich in fine particles, digging it carefully from deposits where the rivers had left behind perfect mixtures. Teams of workers would carry baskets of this moist clay back to workshops. Then, the meticulous process of preparation began. Craftsmen kneaded the clay by hand or with simple wooden paddles and rollers, pressing and folding it repeatedly to remove every air bubble and impurity that could cause cracking later. This kneading could take hours for each batch, as uniformity was essential for strength. Once prepared, the forming began. Artisans would roll the clay into long, cylindrical shapes. Some used wooden mandrels, straight poles carved from local timber, to ensure consistent inner diameters. They rolled and pressed the clay around these forms, building up the walls evenly. With wet hands or smooth reeds, they meticulously smoothed the interiors, creating surfaces that would allow water to flow without turbulence or blockages from rough spots. The exteriors were shaped for durability, with walls thick enough to withstand the pressures of burial and soil. Now came the critical step of firing. These pipes were placed in primitive kilns, dome-shaped structures built from mud brick or stone, fueled by wood, reeds, or even dried animal dung. Workers tended the fires with great care, slowly raising the temperature over many hours, watching the color of the clay shift from damp gray to a glowing red, and finally to a hardened buff or reddish terracotta. They monitored the kiln closely, adjusting vents to control airflow and prevent uneven heating that could shatter the pieces. A successful firing might last an entire day or more, requiring constant attention through the night. The result was durable, fired clay pipes that could last for generations. Joining these sections required ingenuity. Artisans crafted male-female ends, where one pipe's narrower end fits snugly into the wider end of the next. They sealed these connections with bitumen, a natural asphalt that seeped from the ground in certain areas, or with specially prepared clay mortar. These seals were pressed firmly and allowed to dry or cure, creating watertight joints. Installation was an enormous undertaking. Workers dug trenches by hand using wooden shovels reinforced with bronze edges or simple stone tools. They laid the pipes in straight lines or along gentle slopes. Gradients were calculated by eye or with basic water levels. Long troughs filled with water to check evenness. The goal was consistent gravity flow, allowing water to move naturally without pumps. Pipes carried fresh water from canals to fields and temples, while others served as drains, removing waste from early latrines in important sites like the Temple of Bel at Nippur or at Ishnana. Challenges were ever present. Floods could erode trenches and expose or damage pipes. Animals might dig around them. Sediment and debris could cause blockages. Solutions included regular maintenance. Workers would crawl through larger conduits armed with brushes made from bundled branches or reeds to clear obstructions. Overseers coordinated hundreds of laborers, a mix of skilled craftsmen and workers, including slaves, using measuring rods and verbal commands to maintain alignment and depth. The entire process was slow and labor-intensive, yet it laid the foundation for organized urban life. Now, let us travel further to ancient Egypt around 2500 BCE. Here, plumbing advanced with the introduction of copper pipes, discovered in pyramid complexes and other elite structures. Copper mining was a demanding art. Miners ventured into the Sinai Peninsula or along the Nile Valley, extracting ore from veins in the rock using stone hammers and copper chisels. The ore was then smelted in charcoal furnaces. Teams of men operated bellows, large skin bags, or clay tubes, to force air into the fires, raising temperatures high enough to separate the metal. The molten copper was purified by skimming impurities, then cast into ingots or sheets. To form pipes, smiths hammered these sheets around mandrels or cast them directly into tubular shapes. Joints were created through soldering with copper alloys or riveting, requiring precise fitting so that connections could withstand water pressure without leaking. These copper pipes supplied water to pharaohs' tombs, temples, and the drainage systems of worker villages near major construction sites. This plumbing expertise was deeply connected to the monumental pyramid construction, most famously the Great Pyramid of Giza. Surveyors used plumb bobs, weighted strings for vertical alignment, sighting rods, and water-filled levels to achieve perfect gradients and orientations. The pyramid itself stands as a testament to old-school engineering. Quarrying began with massive limestone and granite blocks. Workers used copper chisels to score lines in the stone. They inserted wooden wedges into these grooves and soaked them with water, causing the wood to swell and split the rock cleanly. Blocks were then levered onto sledges. To move them, teams poured water on sand in front of the sledges, dramatically reducing friction so that dozens or hundreds of men could pull loads weighing many tons. Ramps were constructed from mud brick and compacted earth, rising in layers, possibly straight, zigzag, or even spiral configurations around the growing structure. As the pyramid rose, levers and counterweight systems helped position blocks with astonishing accuracy. The workforce numbered in the tens of thousands of skilled laborers, organized in rotating shifts. They lived in nearby villages with bakeries producing bread, breweries making beer, and medical facilities. Everything was coordinated with military-like precision under the direction of architects and overseers. Internally, the pyramid features precise passages and the king's chamber, aligned to cardinal points using astronomical observations of stars. Over 20 years, approximately 2.3 million blocks were placed, some granite beams weighing up to 80 tons, achieving joints so tight that a knife blade could scarcely fit between them. All without modern machinery, just human ingenuity, organization, and persistence. Moving onward to the Indus Valley Civilization, also flourishing around 2500 BCE in what is now Pakistan and India. This is where plumbing truly reached remarkable sophistication. The planned cities of Mohenjo-daro and Harappa featured standardized baked bricks of uniform size, wide streets laid out in grids, and an unprecedented sanitation system. Every house had private bathrooms and toilets connected to covered brick drains. The pipes themselves were terracotta sections, often fitted with inspection holes for easy access. These sloped gently to central sewers that carried waste to rivers or soak pits outside the city. Construction reflected strong central authority. Bricks were fired in large kilns, with workers stacking them precisely in kilns fueled by wood, controlling drafts for even baking. Drains incorporated corbelled arches for added strength without collapse under soil weight. Manholes allowed maintenance crews to enter and clear debris. The crown jewel was the Great Bath in Mohenjo-daro, a large, waterproofed pool lined with bitumen, featuring steps for access, changing rooms, and sophisticated drainage. Workers tested water flow before covering channels, ensuring no leaks. This system supported dense urban populations, dramatically reducing disease and demonstrating old-school civil engineering at its finest. Imagine the satisfaction as clear water flowed through newly completed channels for the first time. Roman engineering elevated pipes and water systems to unprecedented scales. Consider the first major Roman aqueduct, the Aqua Appia, completed in 312 BCE. Engineers sourced water from distant springs, carefully surveying routes over many miles. They employed the groma, a cross-shaped instrument with plumb lines for straight alignments, and the chorbates, a sophisticated level, to achieve incredibly gentle gradients, sometimes as slight as 1 in 4,800. This prevented destructive erosion while maintaining steady flow. Conduits were built underground where possible, using stone, brick, or the revolutionary opus cementitium, Roman concrete. This material mixed pozzolana volcanic ash with lime and aggregates. Workers measured precise ratios on site, treading the mixture by foot or with animals in large pits until it reached the perfect consistency, then pouring it into wooden formwork. It hardened into a mass stronger than many natural stones, resistant to water. For valleys and dramatic crossings, they constructed arched bridges like the iconic Pont du Gard, standing 160 feet high with 3 tiers of arches. Stones were precisely cut with iron tools, dressed on site. Cranes powered by tread wheels. Large wooden wheels turned by teams walking inside, and pulleys lifted them into place. Many arches used no mortar. The precise wedge-shaped voussoirs locked together by gravity and geometry alone. Where necessary, inverted siphons used lead pipes, called fistulae. Sheets of lead were rolled and soldered with lead tin alloys, sometimes reinforced with concrete encasements. These pipes crossed low over valleys before rising again, maintaining overall gradient. Labor involved legions of soldiers, skilled slaves, and free craftsmen under engineers like Vitruvius, who documented methods in detail. Aqueducts could deliver up to 40,000 cubic meters of water per day. Distribution occurred through castella, settling, and distribution tanks, then smaller lead pipes to public fountains, homes, and grand thermi baths heated by hypocaust systems with underfloor hot air circulation. Challenges included leaks at joints, mineral deposits known as sinter that narrowed channels over time, and repairs requiring temporary diversions. Yet these systems supported a city of over 1 million people, with fountains flowing freely and public hygiene far advanced for the era. Consider the Colosseum, that colossal amphitheater. Foundations were excavated in marshy ground with extensive drainage systems tied to aqueducts. Travertine blocks were quarried, transported by barge on the Tiber and Oxcart. The concrete core used similar pozzolanic mixes. Wooden sintering supported vaults and arches during construction, removed once keystones were placed. Hoisting employed capstans and pulleys. The structure seated 50,000 spectators and could even be flooded for mock naval battles using aqueduct water. For river bridges like the Ponte Fabricio, builders used cofferdams, double-walled wooden enclosures driven into the riverbed, pumped dry by manual or animal-powered devices. Piles were driven deep, and concrete poured underwater thanks to pozzolana's properties. Arches rose symmetrically from piers for balance. Principles echoed across wonders. Precision surveying with basic tools, material innovation like concrete and fired clay, massive coordinated labor forces, and reliance on gravity. These enabled thriving cities, reduced disease through sanitation, and symbolized imperial or royal power. In later periods, similar techniques persisted in medieval aqueducts and fortifications, always building on those ancient foundations of persistence, ingenuity, and careful observation of nature. As we conclude this journey, reflect on how those first humble clay pipes, shaped by hand in Mesopotamia, sparked a revolution. They enabled the pyramids' precision, the Indus city's hygiene, and Rome's grandeur. These ancient builders, with their sweat, ingenuity, and vision, laid the literal foundations for modern infrastructure. Let us appreciate their legacy deeply. Thanks for watching. Subscribe and turn on notifications so you don't miss the next incredible story from history's greatest builders and civilizations.